This is problem 10 from chapter 13. It's on page 502. A spacer made of SAE 1020 hot-rolled steel is in the form of a hollow cylinder with a nominal inside diameter of 3 1/4 inches and an outside diameter of 4 inches. It is to be mounted on a solid steel shaft with a heavy force fit. Specify the dimensions for the shaft and sleeve and compute the stress in the sleeve after installation. Use the basic hole system. Alright, so let's write down what we know. We're told that the spacer, this is 10. The spacer looks something like this. It's hollow. It has a nominal inside dimension that has diameter 3.25 inches. Now that's up to us. It doesn't have to be exactly that. We can change it. But the outside dimension is exactly 4.0. They gave us that number all the way down to the third decimal place in size. So there's the size of it. Now, of course, the shaft, so there's the hole, the shaft would nominally be a diameter of 3 1/4 inches as well. Of course, since we want a heavy force fit, well then the shaft is going to have to be bigger than the hole. Okay, now we know further that the spacer is made of SAE 1020. Okay, so we're supposed to use the basic hole system. That means that this hole could potentially take on the size of 3 1/4 inches. Alright, so we have to select a force fit, and they've asked us for a heavy force fit. So let's go back and look for a specification that will give us a heavy force fit. So go to page 495 and look at table 13.4. So here's force and shrink fits. They've got an FN1 all the way through an FN5. But which one is considered to be a heavy force fit? Well, let's find out. Go to the next page, page 496. They've got FN1 light drive fit all the way to FN5 force fit. Now, the way it's described, FN3 in the center is described as a heavy drive fit. FN4 force fit used for high strength assemblies where higher resulting pressures are required. FN5 similar to FN4 for higher pressures. Now, I don't know exactly what they mean by a heavy force fit. I assumed that they meant FN5. So that's what I'm going to design as an FN5. So that controls how much interference and potential, minimum and maximum there's going to be on this thing. So go back to, let's find it quickly, the page with the force fits, page 495. And the nominal size is 3 1/4 inches. Now that 3 1/4 inches is between, 3.15 and 3.94. This is page 495. Let's see, it's the 1, 2, 3, fourth row up from the bottom. And if I'm going to design an FN5, that's the column all the way over on the right hand side of the page in the table. And so there the standard limits for the hole are plus 2.2. So the hole plus 2.2, and this is thousandths of an inch. So really you could write it this way, plus 0.0022 all the way down to plus 0. That's the lower limit. And they say minus 0. In other words, no less than 3 1/4 inches. And if we're going to use 4 decimal places in the previous, we should there as well. And for the shaft, it says the shaft should be oversized by anywhere from 8 1/2 thousandths all the way up to, 8 1/2 thousandths is the high end. So anywhere from 7 thousandths all the way up to 8 1/2 thousandths. Okay? So if we were to consider what that means that the whole specification, and let's just modify this, so let's add the 2 1/2 thousandths. The whole specification is going to be anywhere from that, 3.252, 2 actually. Okay, so it could be a little bit larger than the basic size. All the way down, it takes care of this one, to 3.2500. So the hole could actually be oversized a bit, and that would be okay. But notice that the shaft is always oversized more than the hole. The shaft, the 7 thousandths here is going to give you what, 6.8 thousandths over at least. So the shaft is going to be anywhere from 3.2585 all the way down to 3.2570. So there are the specifications on the size of the hole in the shaft. Alright, now we're supposed to specify the dimensions, we've done that, and compute the stresses in the sleeve after installation. Now there's a couple different ways of installing these things. You could just drive the two together, which is not going to be easy with this much interference. Or you could heat up the hole to make it expand and cool down the shaft in order to make it shrink. And then you can slip the two together. So this is quite a bit though. This is a pretty heavy fit. So even after heating one and cooling the other, unless you attain some pretty extreme temperatures, I think you'll still have a decent drive fit here. Anyway, we've got to calculate the stress, and we need it in the outer member, and did they ask for it in the inner member? Let me see. I don't recall. Compute the stress in the sleeve. So they just want the stress in the sleeve. In order to get that stress, we will have to calculate the pressure. Go to page 496 and look at the procedure for computing stresses for force fits. It's over in the lower right hand side of the page and goes into the next page as well. So once the two are together, basically this point here is what they call, or this dimension here is what they called B, because this is going to be on the shaft. And A, notice, is equal to 0. A is the size of the hole, it's the radius of the hole in the shaft. And notice A, B, and C are all radii, they're not diameters. Be careful about that as well. So, in fact, B is going to be half of this. In any case, A is 0 and C is the outside radius. So this tells us that C is 2.0 inches. Okay, so that's definitely the size of C. We've got that one. But B and A are but B is something we have to figure out, to consider. All right, now the equation for pressure, there are actually two. There's equation 13.2 and 13.3. And 13.2 is for when the sleeve, in this case, and the shaft are made out of the same material. Equation 13.3 is for when they are two different materials. We are not told the material of the shaft. The best we can do is assume that both are the same material, SAE 1020. So to calculate the pressure, we'll use equation 13.2. And it looks like this. We need the elastic modulus, the maximum, we need the interference between the two. We'll talk about that in a moment. To B multiplied by C squared less B squared, quantity multiplied by B squared less A squared, divided by 2B squared, C squared less A squared. Okay, now note A is equal to 0. In other words, there's no hole in the shaft, so that's gone. And we have to decide what C and B will be. Now C is exactly 2 inches, but what about B? I mean, how do we define B? Because do we have to calculate exactly how far the thing will actually stretch and calculate the pressure and then make sure it balances on both and iterate? No, we're not going to do that. It's not necessary. For this calculation is not terribly sensitive to the B parameter. Okay, as a matter of fact, in this particular example, notice that these two would cancel. There'd still be here, and even if they didn't cancel like this in part, it's still not sensitive. Okay, so we don't have to worry about it too much. I will make the simplification so I don't have to write as much. What's really interesting, and what the pressure is really sensitive to, is the interference. And so if you think about this, you realize, well, if the hole is the largest size it can be and the shaft is the smallest size, that's going to give you a totally different pressure than when the shaft is the maximum size and the hole is the minimum size. That's a totally different situation. So what we're going to do is we're going to take delta to be the max so we can figure out the max pressure and then calculate the maximum stress. That's the point we would be concerned for. So the maximum interference, if you stop and think about it, you'll realize that the maximum interference is, looks like I used 8.4 thousandths, and the reason I did that, you know what, I bet I copied the wrong number. Let me try again. FN5, yeah, I did. This should not be a 5, that should have been a 4. That's my fault. I don't know how I copied the wrong number or changed it in my brain, but anyway, that's correct. So the maximum interference would occur when the hole is the smallest size and the shaft is the largest size. And you can tell the difference between these two is just 8.5 thousandths, so 0.0084. And I said 8.5, I'm sorry, I mean 8.4 thousandths. That's the maximum, right? Because that's the biggest the shaft could be and the smallest the hole could be. So there's our maximum interference. That's what we'll put in order to get the maximum pressure. All right, so we need the elastic modulus of 1020. It's just steel, so we could use, let's see if they have anything a little more accurate. Steel its elastic modulus is something you should commit to memory, and that's 30 E6 psi. And I'm looking in the book to see, I haven't thought of this until now, to see if they have elastic moduli for various materials, because it does vary a little bit, but not a whole lot. And I don't see it in here. It may be somewhere else in the book, but for the sake of this chapter and for what we're doing, using an elastic modulus of 30 times 10 to the 6th psi is fine. The interference we know is 0.0084, that's the max interference, divided by 2b, where b, now like I said, we don't have to be too careful about it. It's not like we have to decide between 3.25222 over 2 or something else. It doesn't really matter. We're going to take 3.25 in half. Okay, that's close enough for b. So 3.25, if we divide that by 2, we would get 1.625 inches. That's just 3.25 over 2. Think about it, it's 1.5 from the 3, okay, plus 1/8 of an inch, 0.125. So that's 1 5/8 inches. So that takes care of this first part, and now we'll add in the geometry here. So c squared, what is c? Well, that's 2 inches. So 2 squared minus b squared, 1.625 squared, divided by 2 times, let's see what was left, c squared. So c is 2 inches, so there we have it. Okay, now let's see. Yeah, I did all that right. All right. When I took these numbers and plugged them into my calculator, notice that I forgot units here. This is inches. Notice the inches there cancel, and I haven't written any units here. The reason is because all of these units cancel. We have a term that will be inches squared and a term here, inches squared. And so this second term in the square brackets is dimensionless. So all we'll be left with is PSI. In fact, that pressure comes out to 13,174 PSI. So there's the pressure, but we weren't asked for the pressure. We were asked for the stress in the outer member. As I said, we had to calculate the pressure first because the stress in the outer member, the equation for that, depends on the pressure. So look at page 497, still in the procedure for calculating stresses for force fits, and you'll see equation 13.6 allows us to calculate the stress in the outer member. That that's the deformation. Let me back up. It's equation 13.4. Notice the subscript O stands for outer member and the subscript I stands for inner member, or in other words, this is the I, the inner, and this is the O, the outer. Okay? All right, so the equation is that the stress in the outer member is equal to the pressure multiplied by c squared plus b squared divided by C squared minus B squared. Well, this is pretty straightforward because we have the pressure. It's 13,174 psi. C is just 2 inches, so 2 squared, plus B is 1.625 squared, divided by C squared, 2 squared, less B squared, 1.625 squared again. Okay, so that should give us the stress, and when I plugged all of this in my calculator, I got that stress was 64,363 psi. So there's the answer they asked us for. So that's the stress. If the strength of the sleeve is less than this, it's going to break because there's more stress in it than it can handle. Let's find out just for interest's sake. Let's look up 1020. Make sure we get the correct description from the problem statement. It is 1020 hot, this is 10, hot rolled steel, 1020. Let's go look up the properties and find out. So go to the back of the book in the appendix, and let's see, the steel properties. I'll find that in a moment. I just thought to do this. Here we are. Okay, page 725 in the appendices, appendix 3. Has material designation number, the SAE number. The first 3 are 1020, and hot rolled is the first. Well, notice that the yield strength is 30, so definitely, or 30 ksi. So this is way above that. It's definitely going to yield. But notice that the tensile strength, the ultimate strength of this material, is only 55 ksi. The 64 ksi will definitely break the sleeve. So we can tell that this design will not work if we have 8.4 thousandths of interference. Now, it's possible that we would have less interference. That's going to take down the pressure, which would then take down the stress. So some of these are going to break, maybe, and some of them won't. I don't know. What you could do at this point, if you wanted to get a little more practice with this, is go through the calculation with the minimum interference. So assume that the shaft is only 7 thousandths over, and that the hole is also 2.5 thousandths over. So the difference between those two would be, what, 4.8? So you'd have 4.8 here instead of 8.4. Interesting, that's just reversed. So 4.8, and that's going to be about half, and this would come out to about half. So if my approximations are correct, then that would still be above 30,000 psi, and it would still yield, which is not acceptable. But like I said, it is possible that you would have this much interference and it would break. Now, another possibility, notice I chose an FN5. We could decrease that. Maybe a lighter force fit would be acceptable, where it would be guaranteed less interference. If we could get away with it, then that would be fine.